How we doing? Hopefully better than me right this second. I don't understand why this is having so much issues. I just recorded my last lecture, and of course it just deleted it. But, so that's good for anybody who wasn't here. That's awesome. Do you have homework for me? Excel part. Thank you. Oh, yep, thank you. Thank you. Questions about anything? Yeah.
Do we need to be able to do all this stuff that we're doing in Excel by hand for the test?
No, I want you to do it in Excel.
Okay, that's what I thought.
Yeah. Absolutely, 100% want you to use it with Excel. Yes.
Okay.
Yeah. I want you to be able to use the tool. So, don't do all of that. What's that?
I said I did that yesterday. I figured I should know how long it takes.
No, I don't want you to do it by hand. All right. I mean, you do need to know the formulas so that you're using Excel, but yeah. Now, as far as the actual doing all the things and computing all those things, yeah. All right. So, well, let's continue on then with more confidence intervals. So, the last thing we talked about was confidence intervals for, oops, I am recording. Okay, good. Confidence intervals for variance. I believe I'm recording. Yeah, it says I'm recording. Good. Just make sure. So, one of the assumptions that we make, pardon me, when we're doing confidence intervals for differences of means, when we have small samples, is that the variances of the populations are equal to each other. So one of the things that we're going to want to be able to check is if, in fact, the two variances, or we at least have some justification for making that assumption. Actually being able to test that the variances actually are equal would be really difficult. Proving something that one thing is actually, from a statistical standpoint, proving one thing is equal to another thing, is literally equal to it, would be really, really difficult. Now, having no evidence to say that they are different is a different question. Okay. So, like for example, when we've done the confidence intervals for differences of means, we're not saying that the two means are the same based on our confidence interval. What we're saying is that if we've got some values in our confidence interval that are negative and some that are positive, we really can't tell if they're the same or if one's bigger than the other. We don't have enough evidence to say one of them is bigger than the other, right? We're not saying they are in fact equal. We're just saying we don't have any evidence to say that they're not. It's a different statement, but there is a distinction between those two things. So likewise for variances, we make assumptions about the variances being equal, or at least being close. And we want to make sure that that assumption of the variances being equal isn't outlandish, essentially. Okay. So what we're going to do is talk about how we come up with a confidence interval for a ratio of variances. And then based on that confidence interval, do we see 1 in the middle? Because if the ratio is 1, then they would be equal. So if you've got some values for your confidence interval for the ratio that are less than 1 and greater than 1, then you would have no evidence to say that they're not equal. And then you could go on with your assumption that they are. Versus if you come up with your confidence interval and you've got the ratio is much bigger than 1, all the values are bigger than 1, or all the values are smaller than 1, then your assumption wouldn't make any sense. So that's the idea behind what we're getting ready to do for this. So we're still in section 6.4. This is just towards the end of it. Pardon me. So what we want here is we're going to start with the following random variable. We typically refer to it as f. The random variable that we have here is going to be this one. So we're going to do our typical, well, I got more to write on here, by the way. So this is going to be our typical chi-squared random variable that we talked about. So this is taking the sample variance for y, dividing out the population variance for y, and multiplying it by m minus 1. That gives us chi-squared on that many degrees of freedom, right? That's a chi-squared random variable with m minus 1 degrees of freedom. So then this, if we divide by, if we divide out by its degrees of freedom, which I know will cancel, but there's a reason why we're doing this, and then do the exact same thing, but for your x's, and divide out by its degrees of freedom, this is what's referred to an F distribution. We probably mentioned it last semester. I can't remember if we did or not, but it's definitely been a while. So just to remind you the definition of an F distribution, pardon me. So an F distribution looks like this. This is an S. So U is chi-squared of R, and V is chi-squared of S. So it's a ratio of chi-squared random variables divided by their degrees of freedom. That's where an F distribution comes from. Remember, the T distribution that we had was standard normal over the square root of a chi-squared divided by its degrees of freedom. That was a T. That's where we got our T formula came from. So this chi-squared divided out by its degrees of freedom piece is something that we've seen before, at least for a T distribution. So that's what an F distribution is in general. So that's why we've got this funky formula on the for the F thing that I've written here for the variances. All right, so that's why this is an F distribution. Pardon me. Usually the Usually the notation for this is F with R and S. So the R is referred to as the numerator degrees of freedom, and the S is referred to as the denominator degrees of freedom. I got a tickle in my throat, sorry. Pardon me. Try another drink of water. All right, so in this particular case, for the F distribution we wrote down for the variances, the degrees of freedom for your numerator is 1 less than the sample size for the y, or whatever you're putting on top for the ratio. It doesn't matter if the y or the x goes on top or bottom, you just have to make sure you keep track. So your numerator degrees of freedom here is the 1 less than the sample size for the y sample, and then n minus 1 will be, or the degrees of freedom on the bottom will be 1 less than the x sample. That's if you're doing y over x that you're trying to get the ratio for. The reason why I'm making a big deal out of this is for two reasons. One, you got to make sure you put the numbers in correctly into Excel or when you're looking up the table in the back of the book. The second reason is things are going to flip here in a second when we get our confidence interval. Okay. The numerator and denominator degrees of freedom will be the same as they are with this setup, but we're going to have to do a reciprocal of something, so it's going to flip-flop some things. Okay, that's the only reason why I'm making a big deal about it right now. All right, so notice here that we get our degrees of freedom cancel, right? Okay, so this becomes sy squared over sigma squared y and sx squared over sigma squared x. All right. So again, we want a confidence interval for a ratio of the variances. So if we do that, again, we want, just like we've done before, we've done the probability that our random variable that we have is in between two values is equal to 1 minus alpha, just like we've done before. So now if we simplify and move some things around, notice that your variance for x and your variance for y end up flip-flopping, right? Right? And then if I move things to the other sides of the double inequality, you're going to have an sx squared over an sy squared in both places. So things are flip-flopped. Now I'm going to finish this off here in a second, but we started with the f random variable in the middle here, right? So that f random variable that's in the middle, these values that we're going to use for C and D are going to be the same types of percentiles that we used for normal and that we used for chi-squared, right? Those are the same percentiles that we're going to use, right? We have the alpha on the tails, we split it in half, and we have a lower percentile value that we use and an upper percentile value that we use, right? It's going to be the same idea, but we started here with the y and the x being on top and bottom respectively, which means that your numerator degrees of freedom here is still the y tied to the sample for y, and your denominator degrees of freedom here is tied for the sample for x. However, the confidence interval we're coming up for is a ratio of x over y, right? So this is where, like I said, you have to be a little bit careful. It's easy to flip-flop because you're thinking x over y, and when you do these values for the f distribution, you might use the wrong numerator and denominator degrees of freedom, okay? I'll show you what I mean here in a second, okay? But this says x over y, so you might think your numerator degrees of freedom is tied to x, right? But it's not. It's tied to the y because that's where we started. Okay. So this c value and this d value, just as for the c and the d, this is going to be your 1 minus alpha over 2 percentile for m minus 1, n minus 1 degrees of freedom. And this is going to be your alpha over 2, m minus 1, n minus 1 degrees of freedom. So then that gives you your confidence interval right there. I mean, it's the confidence interval for x over y, variance of x over variance of y. Remember, again, it doesn't really matter since we're doing a ratio, and what we're really concerned with is if 1 is in the interval. It doesn't matter which one's on top and which one's on bottom. Right? Doesn't matter which one's on top and which one's on the bottom. But what does matter is when you're trying to find these values on the sides. So when you're doing the confidence interval, when you're doing x over y here, the x really started out in the denominator, is what I'm saying. Okay, even though it's in the numerator here when we're doing this because of the reciprocals. This is why I'm making a big deal out of it, because it's easy to flip-flop it. All right, so let's see if we can do one of these. Oh, I have a homework assignment for this. I'll write it down here in a second. I forgot I had to have a new homework assignment. I got distracted with the fact that my entire recording got deleted. Not very happy about it. What am I doing? This is, let's do 6.4-13. Type some values in here. All right, so for x's, we've got a few observations here. 15, 23, 12, 18, 9, 28, 11, and 10. Those are our x observations. I'll just leave a column in between for the y's here. We have 25, 20, 35, 15, 40, 16, 10, 22, 18, and 32. Not sure why I did that. All right, so for each of these, we need to know the x variance and the y variance, and then the sample sizes. This is sample variance again, so we'll use, so I'll use the variance.s, and I want to go from A1 to A8, and then the same thing for the y. Except I want to do C1 to C10. Oh, for heaven's sake, why can I never hit the O? It's always the P, every single time. That was, I need the C, darn it. All right. Of course, if I had a mouse, I would just go over and drag it across, so I wouldn't bother typing it in every single time. All right. So the x variance, the y variance, and the sample sizes. The other things that we need, of course, again, are the percentile values, right? Just like what we did for our z sub alpha over 2, or our t sub alpha over 2, or for our 2 chi-squared values that we need those for the F distribution. Good news is that, of course, it's built into Excel. So let's do the, I'm just going to call it F lower and F upper, just so I don't have to type alpha every single time. You can label it however you want, as long as I understand what it's supposed to be. All right. Again, just like the chi-squared distribution, your F distribution starts at 0 and then has a bump and tails off at the end, right? So it's not symmetric about anything. So just like chi-squared, we have to have a lower value that we compute and an upper value that we compute. And on Excel, there's an F dot inverse and an F dot inverse dot right tail. Okay. So we can do the same thing like we did for the chi-squared and just use the two different commands to get what you need. So I'll do f dot inverse first. The probability here, they want a 95% confidence interval. This actually asks for a one-sided, but we're going to do two-sided. 95% confidence interval means our probability will be 0.025. So we have to split the alpha in half, right? The first thing that goes in is your numerator degrees of freedom. Now again, it matters which one you're going to put on top and which one you're going to put on bottom. Okay? I don't really care how you construct the confidence interval as long as you get the right percentiles with the right ratio. Okay? So if you're going to do x over y, then to do your calculation for your statistic, then your degrees of freedom are y comma x. It's reversed. Okay? If you're going to do y over x for your statistic, then it's x over y, or x comma y for your degrees of freedom. So to keep it consistent with what you have in your notes, let's do x over y for your statistic, so it's y comma x for the degrees of freedom. So your denominator degrees of freedom, or excuse me, your numerator degrees of freedom go in first. Numerator is y, so it's going to be f4 minus 1. And denominator will be x, so it'll be f3 minus 1. Okay? And then do the exact same thing, except do the f dot inverse dot right tail. Again, 95% confidence interval says that we are doing a 0.025 for the tail. Still same degrees of freedom. We'll do f4 minus 1 and f3 minus 1. Just like for variance, the confidence intervals for the variance, we're going to subtract one off for the degrees of freedom. We just have to do it for both, the top and the bottom. Because, of course, now we have two chi-squared distributions that we're worried about instead of just one. Okay. All right, so that gives us our f values that we need. So now we'll do our lower bound and our upper bound for our confidence intervals, or confidence interval. So again, according to the formula, we'll do our lower f value and multiply it by the ratio of the sample variances. Again here, I know I'm emphasizing this, but it's easy to mess it up, which is why I'm doing it. When we calculated the f lower and the f upper, the lower and upper percentiles, we used y first and then x. Here we're doing x over y, right? But again, this is going to give us the lower bound for the confidence interval of y over x. Okay? Or no, I'm sorry. It gives us the lower bound for the confidence interval of x over y. We started with y over x. See, I told you it was easy to mess up. It gives us a lower bound for sigma x over sigma y, sigma squared x over sigma squared y. But we use y and x for the degrees of freedom. Again, at the end of the day, the big thing is to see if 1 is in your confidence interval. That's what we're looking for at the end of the day, right? The whole point of this, I mean, we're doing this for practice right now to just get the confidence interval. But the whole point of this exercise is that you're trying to test, and we're going to talk about hypothesis testing in, I think, the next chapter. We're going to do it for a couple of chapters, actually. But we're trying to test if an assumption we're making is valid or not. That's what we're testing. Okay? So when we do the t distribution for differences of means, and we have a small sample size, and we want to know, is there a difference in the means, we have to be able to say, okay, if I'm doing this distribution for the t distribution, or excuse me, doing this confidence interval using the t distribution, I need to be able to say the variances are the same. Well, do I have a way to test if the variances are the same, or do I have evidence that they might be the same? And this is what the test would be. This F distribution comes up later on when you're doing more regression things. So if you do, if you take Math 230 in the fall, that you do some regression analysis, and you do what's referred to as a global F test to see if your model that you're making for the regression makes sense. And from that perspective, we'll actually talk a little bit about that. We're going to do a little bit of regression stuff too in here. So we'll talk a little bit about what I mean by does the model make sense. In particular, if you think about just doing a least squares line, if you've done that before, using a linear model to approximate data, whether or not that model is relatively decent, you've got some things that will tell you about how much error is explained by the model. But also, if you're talking about a line, it probably needs to have some slope, right? Well, are you confident that that slope's actually not zero? Because if you're not confident that the slope's not zero, that line doesn't do you any good. Because if you have a zero sloped line, then you've just got this, right? And it's not actually doing any modeling for you at all. So that's one of the things that you're interested in regression analysis with your global F tests ideas, is make sure that one of the coefficients that you're talking about, these slope things, aren't zero. Not that we have to worry about that this semester, but we will talk a little bit about doing hypothesis testing on the slope of a least squares line. It sounds harder than it is. Okay. Because again, we're going to use tools to help us do the computations, like what we're doing here. Not that I don't expect you to understand some of the concepts behind these things, this is why I'm going over it, but from a practical purpose, I don't see the point in making you go through and calculating the variance by hand. That's dumb. Right? Or pouring through all sorts of different tables to look for these different percentiles. That Excel will spit it out. Right? I mean, honestly, if you go to it, I'm certain that if I can find, I'm sure I can find it somewhere, maybe not necessarily in Excel, but I'm certain that if you put this into some statistical packages, it'll write down the confidence interval for you. You don't have to do anything. Now, that's a little bit more than what I wanted you to have the power to do. I do want you to know the formulas right now, but the other stuff is just a waste of time as far as that goes by doing those things by hand, which is why I want you to be able to use Excel on the test. Right. So again, if we were writing this down, this, you can actually write this on here, you would write, as a double inequality, you would write the 0.1188 is less than sigma squared x over sigma squared y is less than 2.4051. Or if you were writing it as an interval, you would write it this way. And then just like what we talked about for confidence intervals for standard deviations, you would just take the square root of both of these to get a ratio of the standard deviations. Except take the square root, so no big deal there. Any questions on how we came up with that at all? Like I said, it's not too bad. Again, let me show you, just to emphasize why I want you to use the technology rather than the tables. Not that the table, I mean, it's important, I suppose, in some respects to make sure that you understand how to use the tables. But for the F distribution in particular, see if I can find one of these here. Okay, here you go. So to read these F distribution tables, to read these F distribution tables, you have to have lots and lots and lots of different tables. because I have to have degrees of freedom for my numerator and degrees of freedom for my denominator, and I have to worry about what the confidence level is, right? So for this one right now, the alpha is 0.1. So that's this one table only gives it to you if alpha is 0.1. And then you have to have the right number of degrees of freedom. Notice it starts skipping things. We don't have 11 or 13 or 14 or 16 through 19 and so on up the line. It's too many data points, right? So if you didn't have the number in the table, then you'd have to approximate the number that you're looking for, probably through linear interpolation. Okay, you'd have to use an approximation. And then you've got this big mass of tables, or you can just use the technology. So there is an F table in the back of your book, and you can use it if you really, really want to, but it's just easier, I think, to use Excel. Oh, and then there's another thing, too, that pops up. There is a relation, it actually is a neat relationship, I suppose, in some respects, but there is a relationship between the x over the y and the y over the x numbers. So if I go back up here again, we calculated this lower percentile by doing f dot inverse of the 0.025 and then m minus 1 and n minus 1. If you do the reverse, if I do the f dot inverse right tail, oops, I need to do one thing before it. If I do the reciprocal of the right-tailed inverse and flip my degrees of freedom, so 8, nope, 7, and 9, I get the same value. So the reason why that works, of course, is because when you do the reciprocal, all it's doing is just flipping around to what the degrees of freedom are. So you just end up with the percentiles get reciprocated for the appropriate degrees of freedom. So to write that down, it's not something that we're going to use a lot, but just to write it down, if you want f of 1 minus alpha over 2 of m minus 1, n minus 1. Actually, the minus 1s don't matter. I'll just write it as r and s. This is the same thing as 1 over f sub alpha of s comma r. The percentile on the left is the reciprocal of the percentile on the right after you flip the degrees of freedom around. This is kind of a neat property of the F distribution. It's more of a, if you're using the tables, it helps you use the tables. It helps eliminate a lot of the things that you would need on the table if you know how to use that reciprocal part, because then you could always just worry about numerator degrees of freedom and denominator degrees of freedom, and then flip as necessary. So you only have to have really, really detailed on one part and not as detailed on the other. That's what it helps for. It's, like I said, it's a neat property of the distribution. But again, with the advent of technology, it's not exceptionally useful. Any questions at all about finding the confidence interval? This one's actually fairly straightforward. It's not a lot of computation you have to do. Ooh, that's fun. Better that it's bound as opposed to loosely you can go everywhere. Any questions at all? Okay. Well, let's look at then the next section, more confidence intervals. So for 6.5, we're going to do confidence intervals for proportions. All right, so in particular, what we're interested in doing is, say we've got a binomial random variable or a sequence of Bernoulli trials, and we're trying to get a confidence interval for the probability of success, the P part. Okay? So if y is binomial with n trials and a probability of P, then we know that this random variable is approximately standard normal if n is large enough. I'll put large enough in quotes, as usual. Let's think about why this is true. It involves some things that we talked about last semester, but let's think about why this is true. We have a binomial random variable. You can think of a binomial random variable as a sum of Bernoulli random variables, right? The sum of Bernoulli trials, if you will. Each one has a 0 or a 1 each time. P is the probability of success. Okay. So the mean for a Bernoulli random variable is just the P. And if you do that n times, you get the n times P, or that's the mean for your binomial. Same idea for the variance. We've got P times 1 minus P is the variance for the Bernoulli. If you got n independent trials, you would add them all together. That's where we get the variance for the binomial. And then take the square root and get the standard deviation. So we're just doing variable minus mean divided by standard deviation. So we're just doing a standardizing idea. The reason why it's approximately normal if n is large enough, again, it's a sum of independent and identical random variables. They're all Bernoulli. They're all the same Bernoulli trial. If you do a sum of independent random variables and you have enough of them, then by the central limit theorem, the sum is approximately normal, right? So we're taking that, this is the sum of a whole bunch of Bernoulli trials. So even though it's a binomial random variable, if we think about it as a sum of Bernoullis, if there's enough trials, that sum will be normal, approximately normal. And so all we're doing is standardizing a normal random variable. So that's where we get the approximately 0, 1. So that's a central limit theorem idea. So even though it's a binomial random variable, that's just central limit theorem. Right? Take something that's approximately normal, subtract its mean, divide by its standard deviation. All right, so let's see if we can rewrite this a little bit, because again, in this form, that's great, it's a normal random variable. However, we're trying to approximate this parameter, the P. Right? The n we'll know. The n is the sample size. So if we have a sample, we'll know what n is. It's the P that we're trying to figure out. For example, if you're doing polling data, the proportion of people who approve of the job the president's doing, the proportion of a population that has a certain genetic marker for a disease, those kinds of things, right? It's the P, the thing that you're trying to approximate, try to get a handle on. So to get the P as the focus, let's divide through by the n. Divide top and bottom by n. You get y over n minus P over, when I divide the bottom by n, to be able to get it under the radical, I would rewrite it as square root of n squared, right? And then your n's would cancel in the under the radical, so you'd have p times 1 minus p over n. So this is still normal 0, 1. This thing that's on the right-hand side of the equation. That's still normal 0, 1. Right? So now we can do a confidence interval just like we did confidence intervals for normal random variables, right? This thing is still normal 0, 1. This is the piece that I'm trying to get a handle on. But going through the same computations that we did for confidence intervals for normal variables, I would want my p to be in between the y over n. I'll make a little bit more room here. The y over n, I would do minus the z sub alpha over 2. And I would multiply by the standard deviation estimate. Oops, not p, sorry. I would do the y over n, and then the same thing over here. Now, notice that this looks a lot like the sample mean minus the z sub alpha 2 over 2 times the standard deviation estimate, right? Or variance of the sample mean, if you will, right? Because it's standard deviation divided by square root of n. It fits that same format, right? Usually, just to simplify things, we will denote this y over n is your p hat. So it's just, and this is sample again, so this is number of successes in the sample divided by the sample size. It's your, well, it's both. It's your maximum likelihood estimator and your method of moments estimator for p. It's your point estimator that you would use. So notice that you have to use the point estimator for your y over n that's out in front here and your y over n that's under the radical. And use it both places. But again, the idea of this is to use your sample statistic to make some inference about the population in general. In particular, make some inference about what the p has to be, the probability of success is. Okay. This part, well, actually the combination of, no, it's this part right here, this standard error part. If you've ever seen any polling, usually they'll say something like 43% of Americans are not in favor of, or whatever, doesn't matter what it is. But you'll see it plus or minus 3 percentage points. There's always some error with polling, right? That plus or minus 3 percentage points in that case would be this error piece that's here. And we'll talk a little bit about, especially for polling, we'll talk a little bit later on about controlling that error. How do we keep that error within a certain bound? What do we need to do? Well, just like everything else, we look at the sample size. Okay. We'll talk about, I don't know if it's the next section or the following one, but we'll talk about that particular idea about how we keep that in there. All right, so let's see if we can do an example here. This is number 6.5-1. There's a machine shop that manufactures toggle levers. There are 24 flawed levers in a sample of 642. And we want to find a 95% confidence interval for the proportion of flawed levers. The production line is what it says. So, in this case, the P is the proportion of flawed levers, right? So what are we going to use for P hat in this case? Yeah, 24 over the 62. Which is roughly 0.03738. Once we have the P hat now, we can figure out what our confidence interval is. We do need the Z sub alpha over 2, but for a 95% confidence interval, that'll be the 1.96 value. So your confidence interval then is this 0.03738 minus 1.96, and then we will do the 0.03738 times 1 minus that over, what goes in the denominator here? The 642. So that'll be less than or equal to the P, which is less than or equal to the exact same expression, just added in the middle instead of subtracted. So if I use the calculator here, oops. The left number here, I get 0.02271, and if I do the other number, so typing everything in right, it's 0.05206. This one literally is just a matter of plugging the things into the formula. This one's not bad. This okay? Now it turns out that for proportions, this is not the only way to get a confidence interval. There's another method that we could use to find a confidence interval that will make these numbers slightly different. So notice I wrote in the directions as find a 95% confidence interval for the proportion. The actual problem in the book says find an approximate 95% confidence interval. The reason why it's approximate is because depending on how you look at things, you might shift the confidence interval a little bit. So I'll send you out a link of a video that I want you to watch that I recorded the last time I taught this class that goes through the discussion of how to create a second confidence interval that's slightly different. The numbers will be close, but it'll be slightly different. Okay? And it's just a different way to approach it. Now the reason why we haven't approached it that way so far is because if you do the same approach for the other types of confidence, for the normal distribution in particular, if you do the second approach for the normal distribution, you get the exact same confidence interval that we started with. So there's not any reason to do a second approach. Okay. So the video will give you a second approach. It'll be slightly different. It's not that big of a deal. It's a slightly different approach. And then we'll also talk about a third way to talk about how to do this as well. Notice that this proportion here, this number here is small, right? Which when this number is small, it cuts into this a little bit, right? Especially if you get this really, really close to 0. This is going to make this margin of error really small, right? Which might throw some things off. So there's another thing that you might do to adjust it when it's small to make sure that you actually get a margin of error and not have something that's just 0. We'll talk about that next time. But I do want you to watch the video. I'll send out that video link this afternoon. It's like 6.5 minutes long. It's not long. Okay. And again, you're not responsible for the derivation. I just want to show you where it comes from, and then I want you to see that there really is a different confidence interval. So that's the whole point of it. Okay. All right. I'll send that out. Let me give you an assignment though over the new assignment there, because I did forget to write that down at the beginning of the class. Let me do that real quick. Oops. So 6.4-14, 6.5-2, 10 and 14, 6.6, 4 and 10, and 6.7, 2 and 10. So this will be due next Wednesday, 17th, is that right? Day the 10th? Yeah. We'll actually get into 6.6 on Friday, and then 6.7 talks about least square stuff. We'll get into that. If not, we'll probably start on Friday and then finish it Monday. All right. Have a good one. See you on Friday, if not before.